I'm very happy to introduce to you the speaker of today, who is Fabian Schneider of Heidelberg Institute for Theoretical Studies. So as you can guess from his name, Fabian was born in Germany, and he did also his PhD in Germany, namely in the University of Bonn, under the supervision of Norbert Langer and Rob Izard. But then he moved to do a postdoc at Oxford University. That was in 2015. And so in 2018, he returned to Germany. So he went to Heidelberg University. Since the beginning of this year, so he has an ERC starting grant. So he's a junior group leader at his institute, and he's currently setting up his own group. Fabian is specialized in massive stars and stellar populations, and so his talk of today is actually related to that, and is titled "The Strongest Magnets in the Universe." So Fabian, please, you have the floor.
Well, thank you so much for this kind introduction, and it is really great to be here. It's of course only sort of virtual and electronic, but it was already great fun to talk to some of you, and I hope that we can continue some of the discussions. So as you noticed, I changed the title a bit because it was just fitting better onto the slide. But what this is all about is essentially this little picture that I have on the front slide. It is about merging stars, main sequence stars, and how you get maybe magnetic fields in this process. And in the end, maybe we will have an idea of what happens to the strongest magnets that we have in the universe. But before I start in the universe, I would like to have a look into our daily life. So this talk is pretty much about magnetic fields, and I thought I want to show you a couple of scales that are interesting in this regard. So one of the lowest magnetic fields that I could sort of really think about was what you can maybe find in a human brain, and it's of the order of 10 to the minus 9 Gauss. Maybe if you think about something that you encounter in your more daily life, maybe in your kitchen, you have a refrigerator magnet, and then the magnetic field strength here is of the order of 10 to the 2 Gauss. Some of you might have had the honor, or well, maybe you have to go into this medical MRI system, and whenever you're inside there, then you're exposed to magnetic field strengths of the order of 10 to the 4 Gauss. Remember these two numbers. I think this 10 to the 2, the refrigerator magnet, and also the medical MRI, because that is something relatively typical that will come back in this talk. And maybe some of you have seen this really fun experiment of a levitating frog, which has been conducted by Andre Geim and Michael Berry. They got the Alternative Nobel Prize for that. So they have a superconducting magnet, and it was strong enough here now to make a frog levitate. And in this experiment, they used a B field strength of the order of 10 to the 5 Gauss. But this is not yet the record that we have set on Earth. And as you can see, you can make many different things fly in a strong enough magnetic field. But the record in the lab is currently at roughly 1.2 times 10 to the 7 Gauss. And you just witnessed, and I hope you could see this also online, what people had to do to get to such field strengths in the lab. And what they do is they have a coil, and they simply produce a really strong current in this coil, and so to get a really strong magnet. But then that is not enough. But instead, what they need to do is they have to collapse and implode this coil. And then in this phase, when you sort of crush everything together, then that's really when you can reach the highest magnetic fields here of the order, as I said, of 10 to the 7 Gauss. And that is currently the record that we have in the lab under what they called controlled condition. And you can imagine that the poor PhD student, they have to clean up the lab after each experiment and rebuild it. But the real record, I think, at least as far as I could figure this out, is an outdoor record by some Russian scientists. And they took the same idea. They took a really strong magnet, put a lot of explosives around it, and then crushed it and really pushed it together to get to field strength of 2.8 times 10 to the 7 Gauss. So you might be wondering, why am I telling you these stories? I mean, A, of course, they're interesting to know and they're fun. But actually there is something that I would like you to keep in mind, and that is sort of this pushing stuff together and then enhancing magnetic field strength. That is going to come back at us later in this talk. But let's go and have a look into cosmic magnetism maybe. So let's get away from Earth and really look into the whole cosmos and study what kind of magnetic fields do you have here. This is just sort of a little cartoon of how our universe evolved, starting with the Big Bang on the left-hand side, through the phase of recombination into the dark ages, galaxies and stars are forming maybe here, and then the present day is on the right-hand side of this diagram. And you can ask what the magnetic field strength in the universe might have been in the different phases. And of course, the early universe cannot really be observed, and there are no measurements of magnetic fields in here, but you can still come up with a couple of theoretical ideas. And then typical numbers would be, I don't know, maybe 10 to the minus 18 up to 10 to the minus 25 Gauss. So it's really nothing there. In the epoch of reionization, when the stars are then finally sort of doing something to the interstellar medium, then again, the magnetic field strength might be similarly low. So there's really nothing that you can not even compare to the human brain at this point. There is now a very first measurement that people could make, or let's say it's rather a non-detection of some lines. And from that, they could set a lower limit on the B field between galaxy clusters and between galaxies. And this is, stands currently, I think, at 10 to the minus 15 Gauss roughly. And then the real measurements, but this is still an artistic impression here of the field lines between galaxy clusters. And then the typical magnetic field strength that you experience of the order of 10 to the minus 6. And you can continue this, maybe have a look into this famous galaxy, and you have the measurements of the magnetic field and even some orientation of the magnetic field throughout the galaxy. And typical B fields that you find here are again of the order of 10 to the minus 6 Gauss or micro Gauss. And maybe if you then look into star forming regions, things are getting slowly stronger. But again, this is really tiny magnetic fields here, nothing serious, and also nothing really that can compare to the stuff that we actually even have on Earth. Let's have a look then maybe into our own sun. So this is the picture of our own sun, and there you can see sort of this magnetic rain going down. So what we observe is a magnetic field loop that stretches out of, let's say, the head of the sun here, and it channels plasma along this magnetic field, and then it can rain down. But the average field strength of our own sun is maybe of the order of a Gauss, but of course not so inside these sunspots here. Inside the sunspots, the magnetic field is stronger, and it can be of the order of maybe 10 to the 3 Gauss. Yeah, so suddenly we are in a magnetic field strength regime that is between a really strong refrigerator magnet and the medical MRI. Earth itself has a magnetic field. Again, let's say on the surface of Earth, roughly a Gauss or half a Gauss before someone is complaining. And of course, this magnetic field, although it's not so strong, it's actually shielding us from the radiation, the cosmic bombardment of our own sun. And it's quite important for us, of course. But this is, again, nothing really too strong compared to what we have on Earth. And of course, this talk is going to be about stars, and in particular massive stars. And I'm showing you one example here. This is Tau Scope. And massive stars in general, some of them have strong magnetic fields. And then we're talking about B fields that are of the order of a refrigerator magnet up to maybe a medical MRI. But this is, of course, nothing compared to the real record holders in our own universe. These are, as far as we know, the strongest magnets that we have. And these are magnetars, sort of highly magnetized neutron stars with magnetic field strength of the order of 10 to the 15 Gauss. So you might be wondering at this point, why do we actually care about magnetic fields? I would just like to give you a couple of examples here, because I think they're really exciting, and there's a lot of things that are coming out at the moment. One example that is probably to the heart of many people in Leuven, and this has to do with angular momentum transport in the interior of stars. And I took the liberty to get a diagram here from Connie's review paper. And what you're looking at is rotational velocities on the y-axis plotted as the astroseismic log G, sort of the surface gravity of a star. And I would like maybe you to think about the astroseismic log G rather as something like evolution. So on the left-hand side, stars are young, and then they evolve to the right side, and then they're rather old. And this is also what you can observe, for example, if you have a look into these main sequence stars, the blue things, and then subgiant RGB stars, and later on the second clump objects with sort of core helium burning stars. So this is a transition from hydrogen burning into core helium burning. And what you're observing here is two different values for each star, and namely what is the rotational angular velocity the period of the stars in the envelope and also in the core. And what you notice is on the main sequence, for example, that almost all objects that are measured here, well, there are some exceptions, almost all are essentially solid body rotators. So the surface and the core are spinning roughly at the same frequency. And then when stars evolve, meaning when the core starts to contract and the envelope expands, then this solid body rotation is broken up. As you can see here now, you have differential rotation between core and envelope. The core contracts, so it spins up, and the envelope expands, it slows down. But then there is a mechanism that later on throughout the evolution of the star, for example, when you have then a second clump RGB objects here, where this difference in the rotation in core and envelope has again shrunk. And so that means there has to be some sort of mechanism in the stars that transports the angular momentum. And of course, magnetic fields, that could be one way of doing this, but there might be different solutions to the same problem. Internal gravity waves, I think, is something that people are studying here too, or maybe something completely different that I even couldn't come up with at this point. I would like to tell you also why this is interesting from a different perspective. It's the same kind of problem. It has to do with the angular momentum transport from core to surface in stars. And here's some a plot, which is also from a review paper now by Norbert Langer, but it goes back to some work by Süß et al. From 2008. And what you're looking at is the specific angular momentum in the core. So again, some measure of how fast the cores rotate. And you have a couple of diagrams in here, but now we're plotting things as a function of the initial mass. And you see initially how the stars in some models rotated at the beginning of the evolution, and then they continued the evolution and finally got down to this bluish triangle kind of curve. And this is what the very first stellar models have shown for the remnants of these stars, sort of the lower mass objects here on the on the left-hand side, they would give you white dwarfs. On the right-hand side, you produce neutron stars. And maybe then if you were even to go further to the right, which is not covered by this diagram, you form black holes. And what you observe, yes, there is some spin down in the core of the star, but there's nothing close to what people have observed for the remnants of stellar evolution, like white dwarfs here on the left-hand side, magnetic white dwarfs, neutron stars. These are some of the youngest neutron stars, and there's some magnetars down here. So you're off by orders of magnitude compared to the theoretical models. And what people then did is they came up with a mechanism that can maybe couple core and envelope. And here I'm showing you results for a magnetic dynamo that they have put into the stellar models. And then you could get down in terms of specific angular momentum of the cores to this red curve. But still, let's say the observed objects appear to be rotating even slower. And there's a similar thing that people can observe nowadays, which has to do with the advent of gravitational wave astronomy. And I find this really exciting. This is from a paper from 2020, sort of from last year. And it's a quite kind of busy diagram. So let me try to talk you through. What you're seeing is the effective spin of merging black holes. And what this effective spin means is you measure the spin of the first black hole in comparison to its binary orbit. And you measure the spin of the second black hole in comparison to its orbit. Yeah? So it's projected onto the orbital angular momentum. And then you combine the two, weight them with the masses of the individual objects, and this is what you call this chi-effective parameter. And then the measurements at the time when this paper was published are given here by these blue stars in star symbols. And you can immediately see that they essentially cluster around in chi-effective of roughly 0. So that means that these black holes spin roughly aligned with the orbit and actually don't spin much probably at all. And this is exactly, I think, what I just described in this view graph before. If you then compare to predictions, this is this red and this magenta lines in this diagram. These are models that would correspond to the blue triangles in the previous diagram, meaning that you can get really fast rotating black holes, and there are even some situations here where you can get them anti-aligned. This is a population synthesis prediction. And then people have played with this. They've inserted into their models something like this magnetic dynamo mechanism here. And then you narrow down this distribution of objects and you find that they all cluster around a chi-effective of roughly 0. And this is then much more in line, let's say, with the gravitational wave observations. And since last year, we also got the second gravitational wave transient catalog out by the LIGO people. And now we have 50 binary black hole mergers here, and this is some inference that they have done on the data. And they inferred now that this chi effective is indeed around 0. It's not exactly 0, but a bit larger than that. But this is essentially telling you also these black holes are essentially, well, slow rotators. And the question still remains the same, why is that? And I'm not going to talk about internal gravity waves or anything, but I really want to spend all the time now of this talk on magnetic fields. And in particular, I would like to spend now the time on where do these magnetic fields really come from. In the sun, if you look into the structure and into its envelope, so this is in the background, the picture of our sun, it has a convective envelope and it has a radiative core. And you know that in this convective envelope, you have turbulent motions, turbulent plasma motions, and you have differential rotation, in fact. And both together, they power a magnetic dynamo process. And this magnetic dynamo then in situ generates a magnetic field that you can then spectacularly observe here on the sun. So I also brought you a little video of one sunspot, and maybe, or I hope that you can see sort of this convective motions at the surface of the sun. So this is real observations, and this is what is generating the magnetic fields here. The situation is pretty much the opposite, let's say, when we're talking about massive stars or stars more massive than 1.5 solar masses. Now you have a convective core and you have a radiative envelope. So if you just talk by analogy, maybe think about the convective core, then we can imagine that this convective core is magnetic. And again, you have maybe this kind of convective motions and differential rotation that can produce some sort of dynamo. And then you get this spaghetti magnetic field orientation, as people have found out in simulations. But the surface of these stars is not supposed to be magnetic at all. You have this quiet radiative envelope, and there should be nothing. However, the observations are really telling us that about 10% of these stars actually do have relatively strong and large-scale surface magnetic fields. So the question remains here for the subclass of stars, where does this come from? Now maybe someone in the audience might stand up and say, yes, but actually you do have also convection in the surface, and this is of course completely correct. So I'm showing you one of these classical Kippenhahn diagrams, where you have the mass of the star on the x-axis, and then you have convective regions indicated on the radius of the stars. Sort of you see that stars develop this convective cores, and previously our sun has a convective envelope only. And you can also observe that there are subsurface convective layers in all of these stars. And in principle, of course, you can have maybe some dynamo mechanism in these subsurface layers, and maybe then these B fields sort of pop up at the surface. And there are also papers on this, if you look into the literature, that try to come up with typical values for the B fields, but they tend to be rather of the order of a few Gauss maybe, and not what people have observed in these magnetic massive stars, where the B fields are much, much stronger. I'm going to come to this in a moment. So what could happen maybe in the radiative envelopes? And there are a couple of ideas, and I already described some of them. There's this famous Taylor-Sprout dynamo mechanism, that has also been employed in some of the models that I showed to you earlier, where you could see that the cores of stars would spin down as a function of evolution. There are other mechanisms that could in principle play a role here. There's a magnetorotational instability. You can think of maybe more generic alpha omega dynamos. And there's also this newer Fuller model that I also briefly explained to you in terms of this gravitational wave predictions. But all of these dynamos, they would rather produce maybe smaller kind of magnetic fields and also local magnetic fields. So nothing like a large scale and a strong ordered magnetic field that you could observe from a far distance. So what people have figured out already from observing many of these objects is, and what they think now is the case for these magnetic stars, is that the fields are fossil. And let me just tell you a couple of the observational key points here. And it's the following. So by strong, as I mentioned, I mean that the magnetic field is certainly stronger than 100 Gauss. So it's stronger than a refrigerator magnet, but not too much stronger than that. So the record holder is a Babcock star, an A0 object, and it has a surface magnetic field of 34 kilogauss. So this is pretty much in the ballpark of this medical MRI system. But most importantly, people have not found any correlations with mass or rotation. And this is why then they claimed, okay, these magnetic fields, they are probably frozen into the stellar structure, and this is why they call them fossil fields. And there's another interesting observational development, and that is it is clear now that there is a dearth of such magnetic stars in close binaries. And close here means binaries with orbital periods of the order of, let's say, 10-ish, 20-ish days. So this is the picture. And I would like now to introduce one model that we've been working on how maybe these fossil and these strong magnetic fields in these magnetic stars came about. In case someone is still considering that maybe some sort of dynamo process is doing this, I think this is pretty much ruled out. And from the observational point of view, this is the lack of any correlation with mass or rotation in these magnetic field strength that people have observed. So this is out of the game, I believe. But there are still two favorite, or let's say two quite competitive suggestions in the literature. One says that when stars form from their molecular clouds, then maybe they can carry some of this magnetization, and it is then also being put into the star itself. In one way or the other, this is one suggestion. And then there's a second suggestion, and you probably have already guessed this from the title of this talk and maybe from this figure, is what happens if two stars merge together and form one object? Could this maybe be the source of some magnetic field amplification process? In both cases, I would just like to point this out, you have to somehow explain why it is only that a small subfraction of all the massive stars of the order of 10% have this strong magnetic fields. This is the big challenge, I think, for these channels. It's of course somewhat more clear maybe that you can get this easier from the merging channel, but I'll come back to this in a moment. So I guess I do not really have to tell anybody in Leuven how important binary stars are, but I think these diagrams here are still really, really nice, and I absolutely enjoy them. In particular, this summary work here by Max Mo and Di Stefano. So it shows you what we think at the moment of what the fraction of single stars, binary stars, triple stars, and even quadruple stars is as a function of the primary mass, or let's say of the most massive star in these multiple systems. And sort of this compilation range is roughly from 1 up to 10-ish or 20, 30, 40 solar masses. And what I really would like to highlight is essentially the single star fraction in this diagram, which is quite interesting. And it ranges roughly from maybe a binary fraction of 60% or so in, a single star fraction of 60% in solar-like stars. So our sun, if you want, has sort of an almost 50-50 chance that we have only a single sun and not a binary sun, like in some of the Star Wars movies. And then in the more massive stars, in particular in the O stars, let's say above 10-ish, 20-ish solar masses, there are essentially no single stars anymore. And this has, of course, quite some interesting consequences, as you know. And that is one of the other diagrams I like to show from this paper. This is the fraction of interacting stars, and interaction really means stars where you transfer mass from one to the other object. Again, plotted as the function of the primary mass. And you can observe that this fraction really goes up. And in case you wonder why this can go up even beyond 1, well, then think about, again, what triple stars and so mean and how you actually do the counting. Yeah? So it's a bit awkward, but essentially what this means is that in the massive star regimes in particular, there is hardly any star that is not going to interact with a binary companion by mass transfer in their life. And this is sort of the significance of the binary world. I also wanted to give you a little maybe a bit better understanding of what can happen, because this binary interactions, they can be really diverse and you can get different outcomes. So what I'm showing you here is the parameter space of different binary stars. And I picked a primary star of 10 solar masses. And then I grouped this primary star with another companion. And the companion is supposed to be less massive. So on the top here, this would be a 10 solar mass companion. And down here, this is essentially, let's say, a 1 solar mass companion. And then you can group them into binaries of different orbital separations. And this is what the x-axis shows you. And then depending on what this initial configuration of the binary star is, you will get different outcomes. So maybe ignore the color in the background here for the time being. But I just want to sort of broadly show you what can happen in binary stars. So there's a large region in this parameter space, essentially that region of the parameter space where you do not see any of this white hatching. And in this part of the parameter space, the two stars are going to transfer mass from one star to the other in a stable manner, and it will just continue for a long, long time. But then there are also these other regions, for example, here in the beginning, sort of this hatched area to the left, or let's say the hatched area in closed binaries. And this is where we expect that the two stars are going to merge completely. And then there's and this is of course what I'm going to talk to you about in a moment. And then there's another region in this parameter space for initially very wide binaries, and they can maybe go into what we call a common envelope evolution. So this is then when one star becomes this giant, a red supergiant, for example, or just a red giant, and it then can at some point engulf its companion. And then the companion suddenly finds itself in the envelope of the star, and this is then what we call a common envelope evolution. And there's a lot of physics and a lot of dynamics going on. And we are working on exactly this phase a lot in Heidelberg too. But today, I'm really going to spend most of my time on mergers. And because I like this diagram a lot, I'll just plot this. This is a Hertzsprung-Russell diagram, and you observe a single starburst population made entirely of binary stars. And you can see it evolve, and you see your standard isochrone that you would observe in such a Hertzsprung-Russell diagram. But then also you see all these different data points that, or the stars that pop up around the turnoff of this cluster. Let me just go back and play it again. You see that all these stars are sort of popping up around the turnoff of this star cluster. So I'm trying to trace the turnoff here with my cursor in case, hopefully you can see this. And these are all these blue stragglers. And there are different types of blue stragglers that can pop up. There can be, for example, those that have accreted a lot of mass and also angular momentum, so they rotate rapidly. And this color here, as you can maybe see from this color bar, indicates the rotation in terms of the critical rotation of a star. So a star that is red in this diagram is almost critically rotating. And then you have some other binary products that became blue straggler stars that live then beyond the turnoff, sort of the classical blue straggler stars here. This is for a single starburst population, but if you were to integrate over the whole population of massive stars that we have in our own Milky Way galaxy, then a couple of years back, people predicted that essentially only, let's say, a quarter of all of these stars, massive O stars in the Milky Way, is going to have a single life, and the rest will do something with their companions. And by the time, at the moment, when we look into the Milky Way system, we were expecting that roughly 8% of all the stars or massive stars that we observe are merger products. And here's sort of the first link that I would like to make into the magnetic massive star world. And remember, the incidence fraction of these magnetic stars was roughly of the order of 10%. So we are all in the same ballpark. Of course, it doesn't need to mean anything, but I think this is already a nice coincidence here that you should maybe keep in mind at this point. So the idea that is out already for more than 10 years in the literature, that if you maybe merge two stars, that in this phase you can produce magnetic fields. And what I also showed you, of course, from this little diagram here is that if you form such a merger product, it will show up as a blue straggler. So what we did back then was we were looking out for a star that looks like a blue straggler and is magnetic. And we found actually two, but I'm only going to talk about one of them. And this is the star Tau Sco that I already showed you earlier. It lives in the Upper Scorpius association, and we have estimated that it is younger than 5 million years, but this Upper Scorpius association that it lives in is maybe of the order of 11 million years, but there are quite some large uncertainties. And so back then in 2016, we suggested that maybe this age difference comes indeed from a merger. And we have made some estimates on how much younger such a merged star would look like. And we found that this could well be in this ballpark. And then the natural question that arises from this is, so does it also mean then maybe that if Tau Sco is indeed such a merger product, could then also the magnetic field come from this merger phase? And this is when we turned then to people, or I turned at the time to people in Heidelberg that were working on different simulations, but they have developed fantastic computational tools, and they use this moving mesh code AREPO, which originally was designed for do large-scale cosmological structure formation simulations. And I'm showing you a little German post stamp here on the right, and this illustrates this illustrious simulation that people did back in the time. And it's a beautiful, I think, a beautiful picture from this computer simulation that they have done with the AREPO code. But we now adapted this code for stellar astrophysical applications. And in particular, what we wanted to do was we wanted to take two main sequence stars that would give us a star that pretty much looks like tau SCO, at least age-wise, from this age difference, from the kind of rejuvenation that it would get from our guesstimates that we had before. And we estimated at the time that we probably need to merge a 9 and an 8 solar mass star, main sequence stars that are relatively unevolved, and then we were hoping to get something that would resemble tau SCO in the end. And this was actually a pretty good guesstimate that we did at the time. And here I'm going to show you briefly the simulation. On the left-hand side, you will see a cut through the equatorial plane, and you see the density. And on the right-hand side, you see now the magnetic field strength. And in the beginning, there was no magnetic field except for some seed magnetic field that we put into the simulations, but this was of the order of a microgauss, so essentially nothing. But then in the merger itself, a magnetic field has been produced, as has been suggested by different people before. And this was, of course, fantastic to see. I'm going to show you a couple of still images of this because then it's easier to see what has happened. But I want to say in brief, we have identified that the so-called magnetorotational instability is acting in this merger, and that this magnetorotational instability has helped greatly in amplifying this magnetic field to a relatively high field strength. Let me switch over to the still images. I think this is easier in an online Zoom colloquium. So in the beginning of this merger phase, what you had is two stars in relative close contact, and there's an accretion stream that goes from the primary star over to the secondary star, and this accretion stream now shears on the surface of the companion. And it is then in this shearing layer where this MRI is activated first. And then if you continue in time, you can see that this magnetic field really starts to build up at the surface of both stars, because the matter is really shearing along the shared, let's say, common potential lines here. And then in the end, the primary star is actually tidally disrupted in this event, and then it forms and merges together to form the whole star. I also want to show, or want to tell you a bit more about the magnetic field amplification process, and that it is not only the magnetorotational instability that is helping here, but we also observed some Kelvin-Helmholtz-like instabilities at the interface of the two cores when they finally merged together. So I hope that you can see this bit in this little view graph here. And there's something else that I would like to tell you about, because this is important for now the further evolution. Let me remove this little plot. And this has to do with the density. As you can imagine, in this binary, there's a lot of angular momentum. And this angular momentum has to, of course, go somewhere. You have to conserve angular momentum. And I'm showing you now the equatorial plane in the top panel, but then also the edge-on view in the bottom panel. And what has happened in this merger phase is after the stars have merged together, angular momentum has been greatly stored in what we call then a torus. So if you look into the bottom right image here, you can observe that there is a little spherically symmetric stellar remnant in the center. It has roughly a total mass of 14 solar masses. And then it has a really thick and a massive torus of about 3 solar masses. And this is also where a lot of the angular momentum resides after the merger phase. But we wanted to know now what happens to this star once it can sort of regains equilibrium and is back on the main sequence, and could it look like tau SCO? Maybe do I have enough time for this? Maybe I'm going to skip the magnetic field saturation at this point, but feel free to ask me maybe later on. I want to rather remind you of this peculiar structure that we have right after the merger. We have a spherically symmetric remnant and this massive torus surrounding it. And there are now a couple of questions that we have to answer, and for which we still do not have really a completely convincing answer. So if anybody maybe here in the audience has some suggestions of how one can maybe do things better, then I would love to hear your suggestions. So we have to ask this first question: what happens to this torus? The short answer is that we believe it will quickly convert into a puffed up spherical envelope. And our reasoning is that the accretion time scale that we estimated for this torus is relatively short. It can be maybe of the order of a year or maybe of 2 years. And then we estimated that most of this torus should have been accreted onto the central remnant. And of course, whenever you accrete matter, you also release gravitational potential energy. And so you heat up the matter itself. And so the question is, can you radiate away or can you cool efficiently to get rid of this, this heat, or is the heat going to stay in your system? If it was able to cool efficiently, then probably what happens with this torus is that it is going to start to accrete onto the central remnant, but probably it rather than forms a thin, maybe accretion disk. But what we estimated is that the cooling is not going to be efficient in our case. And so we think then that most of this heat cannot not escape. And so instead, it's not going to form a thin accretion disk, but rather a really spherically extended and a huge, well, relatively huge envelope around this object. So this is the first estimate or the guesstimate that we had to take here. And the second big question is, what happens to the magnetic field that has been produced now in the merger? And the honest answer, we don't know. All we could do is make some estimates of what could maybe happen to it. And it seems to us that the magnetic field, once it is here, it wants to stay. It's not going to go away that quickly. And then if we assume that the magnetic field is not going to decay away, for example, then we could also make some estimates. And you can, for example, assume magnetic flux freezing. And if you do so, then if you compute the magnetic flux roughly whenever you include 60.9 solar masses of this remnant, which is roughly the mass in the end of the simulation that we had. If you flux freeze this flux to the main sequence, sort of go from this large size that we had at the end of the simulation onto a main sequence size like object, then we would have produced a magnetic surface field of the order of 9 kilogauss. So this was really interesting to us because it means that, yeah, maybe we have found a mechanism that produces the right magnetic field strength for these magnetic massive stars. At least we are in the right ballpark. This still doesn't answer our question what we can do now with this magnetic field, in particular also in our stellar evolution calculations that we wanted to do. In our stellar evolution computations, of course, we have to turn this 3D mess and after the merger into a 1D stellar evolution model. And what we have assumed then in this model is that we have essentially a dipolar field configuration or geometry in our merger remnant. So that means that the magnetic field scales with radius in the star to the power of -3. So this is one assumption that we had to make. And with this assumption, we could then also implement a bit additional physics into our stellar model, but again, on a pretty simplistic model. So we included some form of angular momentum transport through such a large-scale dipolar-like magnetic field. And we have also included a mechanism that allows to couple the magnetic field to the wind. And then this is usually known under the term of magnetic braking. And the question that we wanted to answer in the end is really, so how fast would such a merger remnant rotate once it is a main sequence star again? So this is what we have had to do with the model, and there are big assumptions that we had to make here, and I would like you to keep them in mind. But now back to what our merger model really did in the end. But before I'm going to show you what the merger model did, I would like to show you how a comparison single star of the same mass evolves in the Hertzsprung-Russell diagram. So this comparison star is a star that has exactly the same mass as our merger remnant, 16.9 solar masses. And it evolves just in the standard fashion, as you know, along the main sequence evolution. It runs out of hydrogen fuel in the center, and then it rushes through the Hertzsprung-Russell diagram, through the Hertzsprung gap, becomes a red supergiant, and at some point here, as a red supergiant, it's going to explode in a type 2 supernova. Our merger remnant does something quite different here. It doesn't start really on the 0H main sequence here, but remember, after the merger, so I'm pointing at the moment at this point where the merger starts to evolve off from, it is a star that has a puffed up envelope from this merging phase. That's what we envisioned here. And we have also made another big assumption at this point, and that is we had to decide what is the internal rotational profile of our star. And we followed what our 3D simulations suggested to us, namely that the interior region of the star is pretty much a solid body rotator that reaches almost critical rotation at the surface. So we put this model into solid body rotation and said that the model is rotating at roughly 80% critical in the beginning of this computation. And now we have dumped quite some energy into the star, and it is out of thermal equilibrium. So what happens in the first instance is that you see a thermal relaxation phase in which the star expands and it increases its luminosity quite significantly. And then once it has reached maximum light, and here's something really funny, at this expansion phase, when it then reaches the maximum radius and maximum luminosity, the star spins up. I'm going to come to this in a moment. And thereafter, it contracts. And while the star contracts, it is slowing down. I think this is completely contrary to at least our naive expectations that we had at the time. Usually, if you sort of think maybe about your standard angular momentum conservation experiments that you had in university, sort of this ice skater that puts out the arms and then pulls them together. And whenever you sort of you're more compact, you rotate faster, of course. But this star now did completely the opposite. The whole relaxation phase, it took a couple of years up to reach maximum light, and then of the order of 1,000 years to get back close to the main sequence, and maybe of the order of 10,000 years to then really be back on the main sequence and in full equilibrium. And once the star was back here on the main sequence, it was a pretty much slow rotator in these simulations, which was quite surprising to us. And what was also really great to see for us, that our initial guess of how can we get tau score was not too bad. So we got a star once it is back on the main sequence after this relaxation phase, that in terms of the luminosity, the effective temperature, but also the surface gravity, looked pretty much like tau score, and also like tau score, it is a rather slow rotator, though I should say that tau score is rotating even slower than what our model predicts at this point. And from here on, the star evolves pretty much like a standard 17 solar mass star, as you can see from this comparison to the single star that I showed you earlier. Also, the star evolves to the red supergiant and then explodes in a type 2 supernova. The only difference being the merger remnant here is always somewhat more luminous. And this has to do with the fact that it is more helium-rich on average. The core of the primary star at the point of the merger that has been tidally disrupted and finds itself in the envelope of the new merger remnant. And this is why the envelope of the star, or the whole star in general, is helium-rich, and so it is a bit more luminous. And then in the end, as I said, it's going to form just a standard type 2 supernova probably. So nothing too special about this, but of course, there's still this question about the magnetic field that the star has, and I'm going to come to this in a moment. I want to say again, there are still several open questions in all of this, and you and also we should be critical of all the assumptions that we have made, but we're going to explore them now in the future, of course. Let's come back to the spin evolution of this star, because this is really bizarre, I think. It is expanding, and then the surface starts to rotate faster, and when it is contracting, it spins up. So what has happened here? So I'm showing you a couple of diagnostic diagrams that hopefully are going to answer this question. But what I want you to remember is that this spin down of the star is not because of angular momentum loss, but it can be completely understood in terms of internal restructuring of the star. And the reason is the following. Maybe you should have a look primarily onto the bottom panel here. It's a busy diagram, but it shows the time after the merger, essentially, after we have set up the model, sort of from the left to the right. The relaxation phase, as I said, ends somewhere between 1,000 and 10,000 years. And in this phase, there are a couple of interesting things happening. So I'm showing you different radii. For example, you can see the surface or this whole radius of the star. This is a full line on top here. And then I have indicated different radii, the radii of different mass coordinates inside the star. So this dotted line below here is at 5% mass, and then 20, 50, 80, 95, and so on %. And what you can observe is, if you just follow these streamlines, essentially, that the inner region is expanding. So the core region is going to expand, and the envelope is going to shrink a lot. And what has happened here is the following. In the merger itself, the central density is now higher than what the star really wants to be, or what the star really wants to have as density in full equilibrium. And so it is over-dense, and the core is even also overheated, so it is a bit too hot compared to its equilibrium configuration. And so the inner core has to expand. And at the same time, there's a really thin surface layer. Yeah, so the whole surface layers here that is indicated between this dashed line and the full drawn line of the surface there's only roughly 1% of the total mass of this star. And there's only this tiny fraction of the total mass is sort of essentially doing the whole expansion of this object. So what you can imagine is, and what then is shown by this blue curve here, the momentum of inertia of the star is going to change by quite a bit. And I'm only showing you the momentum of inertia factor, Rg squared in here. And you can see that this really changes by a lot. And if you imagine now, and I can tell you this from the implementations that we have done, our star essentially remains a solid body rotator. And if it remains a solid body rotator, you can compute, but the rotational velocity at the equator of the star is given by its total angular momentum J, mass and radius, and then this momentum of inertia factor. J, as I said, is going to be constant. The mass of the star is also going to be constant roughly during this relaxation phase. And so there's only the radius that can change and the rotational velocity. We have observed a drop of the rotational velocity by a factor of 5. The radius during this relaxation phase roughly went down by a factor of 4, and Rg squared went up by a factor of 20. And if you combine everything together, then this is the whole spin down that we have observed in this phase. Yeah, so it is really just a restructuring of the interior, of the interior, or this weird interior of this merger product that we have observed. So no angular momentum loss in here, but that's all what explains the slow spin. And maybe if you think about an overheated and an overdense core, there was also something else that we observed in this merger remnant, which was quite exceptional. And that is, we found sort of another source of enhanced mixing in the core region that then helped the star to further rejuvenate, sort of to make it look even younger than it really is. And this had to do with the mixing that occurred in the merger phase itself. So I'm showing you a Kippenhahn diagram here. And so it's age on the x-axis, and then you can look into the interior of the star in terms of mass coordinates. So down here we are in the core. You can see this greenish hatched area. This is the convective core of the star. There's even some purple color on top, which is supposed to indicate the convective core overshooting that we have assumed. And you can see that in this thermal relaxation phase, that lasts maybe up to, again, 1,000, 10,000 years, there is a transient convective core that develops. And it has been driven by enhanced nuclear burning. And this enhanced nuclear burning in the center is because the star was too dense and it was too hot in the center from this merger phase. And there was mixing of carbon and nitrogen into the core. So you have the CN cycle that has been activated, and then it burns in a transient fashion and drives this large convective core. And interestingly enough, if you compare, for example, the average helium mass fractions in the primary and into the secondary, and how it has then rejuvenated into the initial merger, and how much more it has rejuvenated then until the end of this relaxation phase, then both of these phases are actually comparable in terms of how much mixing they have contributed. So this is maybe as a bottom line, there's to be expected, maybe there can be expected some significant rejuvenation in the merger aftermath also. It's not only the merger itself that leads to then these rejuvenated stars. I would like now in the last couple of minutes talk a bit about the final fate of Tausco. And so I'm showing you our Van Gogh impression of the merger remnant here. So you can see in color the magnetic field strength, and there are some shades or shapes indicated that are going to, or that it's supposed to tell you the orientation or the geometry of this magnetic field. So that the background picture is the face-on view, and then here's an edge-on view from the side into this merger remnant. And now I would like you to remember again what I taught you in the beginning of how people on Earth have produced the strongest magnets by compressing matter. And now we have a star here with a core that is highly magnetized after the merger. And of course, if this star is going to evolve up to the final phases in a supernova, then this core, when the star collapses, is going to be pushed together a lot. And whenever you assume then magnetic flux conservation in the central region, and we picked out the innermost 1.5 solar masses that is maybe going to go into a neutron star, and if we assumed magnetic flux freezing from right after the merger up to the core collapse stage, right? This is a huge stretch, keep this in mind. But nevertheless, you can then come up with maybe a magnetic field strength for the neutron star of up to 10 to the 16 Gauss. And magnetars are observed to have B fields of maybe up to 10 to the 15 Gauss. So we are right again in the correct ballpark now for magnetar formation of the star. And just to illustrate or highlight this maybe once more, this compression argument. Here, if you take a teaspoon full of matter from this merger remnant, you have you grab maybe 10 grams. But if you take a teaspoonful of matter, of neutron star matter, then you're at 10 to the 9 tons or so. Yeah? So this is this enormous compression that then can also, if you assume flux freezing, magnetic flux freezing, then can also lead to really strong magnetic fields. And this is what people used on Earth, as I said, right, to get these extremely strong B fields. Maybe on the formation rate of these objects, so that people don't get confused, people have estimated that there's maybe 0.3, so the magnetar formation rate of 0.3 per century, and you can contrast this maybe roughly to the core collapse supernova rate of 2 per century, and then you can come up with the ballpark estimate here from this back of the envelope computation that maybe 15% or of the order of, let's say, 10-ish% again of supernovae, they actually form magnetars. And that again is sort of in line with the incidence of magnetic massive stars, but also it should highlight maybe that you cannot expect to have maybe superluminous supernovae from such magnetars, because also our prediction here for the star is it is a slowly rotating magnetar or neutron star that is going to be born from our default model that we have here. But you can maybe get soft gamma repeaters. And nowadays we know that magnetars are also connected to fast radio bursts and so on. So this is quite exciting. Maybe if there are people here that are interested in A stars, AP stars, and highly magnetic white dwarfs, I think by analogy, this channel could also apply to these situations. Maybe I'm going to skip this slide. This was just to show you that magnetic field amplification happens in many, many situations where two stars interact dynamically, common envelope phases, in white dwarf mergers, in neutron star mergers, and now also in merging main sequence stars. So this is something that I think people have expected, and we also observed it now in main sequence stars. So it's not, let's say, too surprising from that point of view. So I would like to leave you essentially now maybe with my summary, and I was running a bit over time, so maybe I can just leave the summary up here, and then I'm happy to take questions. Thank you so much.
Thank you, Fabian. That was a really interesting and very clear seminar. Thank you very much. So if there are any questions, please say it or tell me in the chat, and then I will mention your name, and I'll try to give priority to the somewhat younger persons. So, okay, so there are several people who have questions. I'll start. They're all senior people for now. Okay, I'll start with Pablo.
Hi, Pablo.
Hey, Fabian, long time. So I wanted to ask a bit about the spin down part.
Yeah.
So in particular, in the plot, you're showing more or less the argument applies for that contraction phase, but you have this long phase where the star is essentially restricted to its critical rotation.
Mm.
So don't you have significant mass loss of angular momentum from that phase?
Yes.
How does the initial angular momentum of the star compares to the total angular momentum in the main sequence? What's the fraction?
Exactly. That is exactly the key point of all of this, let's say, problem here. And the point is the following. The total angular momentum that you have right after, or at the beginning of our computation, we set up this star, when we took sort of this shredded merger remnant, the total angular momentum from here to the main sequence is essentially the same, but only in this particular set of assumptions. We have made different assumptions, and then there is actually quite some angular momentum loss, as you say. And the reason, for example, why you cannot store much angular momentum into this merger remnant at this point is, if you assume solid body rotation, and then you have this tiny envelope in terms of mass, but it has a huge radius, and you have this overdense compact core, then in a solid body rotation configuration, you cannot store much angular momentum. And ultimately, with this relatively maybe artificial setup, and this is really the big question here, we were able only to store maybe a few percent, let's say 5% of the total orbital angular momentum of the binary that we had initially. So most of the angular momentum in that argument would have been transported out into maybe some remnant disk that you form when we think that this big torus starts to accrete onto the central remnant. And as then Stephen Balbus said, well, this is what accretion disks do, because we were also worried, of course, about that, well, suddenly we're losing 90% or so of our angular momentum. But he said, well, that's what an accretion disk does, right? It brings matter to infinity and takes all the, it brings matter to the central region and the angular momentum to infinity, essentially. And then you have, in the end, no angular momentum left in the center, but all of this is sort of gone. And he was like, why not? Okay, but of course, we didn't stop there. So we had one assumption here where we took solid body rotation, and then we started the evolution. And then we took also another assumption where we said, okay, let's allow for differential rotation so we can pump in more angular momentum in the structure. And then we decided we use sort of a constant J profile and put in 10 times more angular momentum. And then we got also a star at the end that rotated not exactly 10 times faster than our default model with a solid body rotation, a bit less, because then this is exactly what you mentioned already. There will be mass loss in this phase. So the star here started out with 80% critical rotation, and we matched 80% to essentially this transition region from star into this accretion or this thermally or pressure supported disk that we observed. And then the star starts to rotate, it hits critical rotation. And I tried to indicate this in this little cartoon here, that there is actually mass loss in this phase. And maybe it is primarily then again along the equator, but maybe people can also imagine that there can be some eruptive mass loss or whatever, because there's also quite some luminosity that wants to get out of the star. And so there can be significant mass loss here, and there is also going to be quite some mass loss of the order of a few tenths of a solar mass in this case where we had the 10 times more angular momentum in the beginning of this model. So this happens then exactly in this phase, but then thereafter the evolution is going to be similar, but then you will end up with a star that rotates a bit faster, or actually quite much faster. So maybe let's say a factor of 10 within these assumptions.
Okay. And during this phase of rapid rotation, did you expect it to be like a crazy OE star? Or, well, this is much lower mass. This would be a V, I guess.
Yeah. So again, yeah. So I guess temperature-wise, right, it is 10-ish thousand degrees, 10 to 20,000, somewhere in this range. So that's probably rather a B star. And then certainly if you have equatorial mass loss, the stuff is still going to be around from the merger phase itself. So maybe you can imagine, or maybe there's some bracket E emission or whatever, but this is maybe for an observer to tell me really how to interpret these features. But yes, but also of course this phase is relatively short, so you really have to be lucky to catch the star in this relaxation phase. I mean, this is let's say 10 to the 3, 10 to the 4 years compared to the lifetime of 1 million years or 10 million years.
Yeah, but it's very bright as well.
It is very bright. That's true. Yeah, that makes it easier.
Okay. Thanks.
Welcome.
Sorry, I was muted. Then we go to Abi.
I was going to ask about the mass loss and whether that contributed to this torus and disk, but that's already been answered, so thanks.
Okay, sorry. Okay. Tomer.
Yes, hi. Very nice seminar. Hi. I have a question. I think I asked it before at a different occasion, but I forgot your answer. So you mentioned that there is a dearth of binaries that are magnetic, but there is one that we know of, a very famous one, Plaskett star, a 14-day period binary where at least one of the components is magnetic. And I wanted to know whether this is not, in a sense, telling us that there are additional ways of producing these global magnetic fields, or whether you could even use your merger model there somehow.
Yeah, so probably my answer to this particular star is that I found so much information in the literature that I am personally completely, let's say, irritated at the moment. What is Plaskett star really? I think it went from one of the most massive stars in the galaxy, and then in some papers suddenly it was, I don't know, a few solar massish object or so. So I think there's still quite some question marks on all of this. And maybe to answer this question slightly differently, yes, I think there are more ways to form also maybe global or large-scale magnetic fields in similar dynamic environments, and maybe even then resampling what you have in Plaskett star. So if Plaskett star is, for example, this post or maybe still in a mass transfer phase-ish being binary, then there are probably ways that you can get there. But these ways, I think, would then again involve some dynamical phase where you can really reach these strong magnetic fields. So what I have not shown you, maybe this is what I should show you at this point, how we got to the magnetic field strengths where we are. And that has to do with this magnetic field saturation, sort of where does the magnetic energy come from? And in the normal mass transfer phase in binaries, there is not so much energy that you can take, for example, from any turbulent or differential rotation in this matter on a short time to pump it into magnetic energy. If you have this merger, the situation is a bit different. You have all this energy available for a short time, and then you can trigger this relatively fast or quick growing instabilities, and then you can pump the energy, for example, turbulent energy here in this case, into magnetic energy. So I think you'll need something really turbulent and dynamic to get to such magnetic field strength. But there are ways in which you can get to this also in binary evolution sequences. So we're doing, for example, common envelope simulations with magnetic fields, and we observe similar phenomena in such a dynamic situation. And there are also very interesting things that we're currently learning from them, but maybe I'll have to hold back some of these things at the moment. But yes, so maybe you can think about Plaskett star in such a configuration.
Thanks, Fabian.
Welcome.
Okay, Dominic.
Hi, Fabian. It's Dominic here. Thanks for a really nice talk. Very clear. I was wondering about the prediction of the magnetic field geometry from your merger scenario. So you talked about the dipolar field, but some of these magnetic massive stars have a non-negligible quadrupolar component. Is that useful from the observational side to help constrain this?
Wow, that's a good question, and let's say we don't have really a good answer to this at the moment. So the reason I'm showing you these diagrams here, these illustrations, is to give you sort of an idea of how complicated the B field is in the interior of the star right after the merger.
Yeah.
But then there will be a relaxation phase of 1,000, 10,000 years. And who knows how this magnetic field is going to reorient and restructure its geometry. I can't tell you at the moment, but what I can tell you maybe is that people know what a stable magnetic field configuration looks like. And this is something that I try to put onto one of the other slides, which I sort of, I didn't really talk about this, but this is sort of one of these B-field configurations that John Braithwaite and Hank Sprout found to be stable, and that sometimes the star also finds sort of this kind of configuration on its own. It means you have sort of this dipolar-like red component in this diagram, and then a toroidal magnetic field, which is now given this ring, this gray ring, and then this blue B field that sort of goes around like a helix. And so then this kind of configuration would be stable. Otherwise, they expect that a large-scale magnetic field can easily sort of decay and then be removed. So naively, I would say, well, maybe this is something that you might expect at some point, but then also in this configuration, who tells you exactly where the surface of the star is and how much of the other components are going to look sort of through the surface. So I can only guess at this point. But it's a merger phase. It's quite dynamic. So maybe the geometry is also not simple in the end. Who knows? In Tosco is indeed a really bizarre object, right? It has this incredibly complex topology,
Yeah, it just occurred to me because observers tend to overestimate the dipolar field strength if they ignore the quadrupolar component. So there's a little bit more wiggle room in these magnetic field strengths for sure.
Oh yeah. I mean, I guess from an observational point of view, it's probably always easier to see the dipolar field component.
Yeah.
It's going to be stronger also further out into the photosphere, and maybe the quadrupolar structure doesn't reach out to such strengths. Yeah.
That's great. Thanks again for the talk. Really good.
Welcome.
Okay, Connie.
I'm an oldie, so I was a bit taken by surprise. Anyway, well, Fabian, you know my question, right? It's not more. It's more like a suggestion. Of course, we can see this if we were to have oscillations in these stars, and tau score doesn't have any in tests. So we look. You know that probably seen, but that fact can be used to help estimate the strength and the shape, as Dominic has just asked, in principle. So here's a strong push for you to start working on that, but I know you will.
Yes, I think it's only a matter of time now, right, that we got also the demand power soon in Heidelberg to go after such questions. That is completely right. Also, I'm not sure, probably I also told you already that we tried at the time to see whether our merger remnant that we produced could maybe show some interesting different seismic properties. The reason why it doesn't do so in this particular simulation is the following. We have merged two relatively unevolved main sequence stars, and so they completely rejuvenated, and they produced really in the interior a structure that resembles that of a single star.
Okay.
So if anything, then it looks like, at least from G modes, pretty much like any other single star. However, what is going to be somewhat different maybe are P modes, because we have a higher helium content in the envelope, and then you get a somewhat different sound speed and so on, and then that can maybe affect some P modes. But when we looked into this very briefly just with Jaya and with Rich in Santa Barbara, there was nothing that was sort of popping up immediately that we thought, okay, this is going to be interesting here. But there will be other mergers that are more interesting in this respect. So
yes,
stay tuned.
You can really get upper limits if you look at the mode excitation as well, because here the modes are suppressed. The model is correct. Now there are plenty of stars where modes are suppressed and we don't see them, and we don't understand that at all. But yeah, the range of stellar magnetic strength and shape will also matter on this front. So you have to do it from a sample study, ideally. I agree.
Yeah.
Looking forward to it.
Yes, same here, same here.
Okay, I see that Hugo offered to ask his question during the coffee break. And maybe it's indeed a good idea to let Fabian catch his breath a bit after talking so long, and have first a coffee, and then we will continue to bombard him with questions.